Hi everyone, welcome to our course on Safety Detect in the HMS ecosystem. In this chapter, we will introduce 4 sets of APIs that provide security detection functions for your app. There are SysIntegrity for checking system integrity, AppsCheck for checking app security, URLCheck for checking external URLs, and UserDetect for detecting fake users. SysIntegrity can check whether the device running your app is secure. If your app involves financial payment or sensitive privacy data protection, your app needs to ensure that the device running your app is secure and reliable. After your app calls SysIntegrity, HMS will return relevant integrity information about the device running your app, so you can check whether the device is rooted or contains Trojan horses and backdoors. Next, let's look at AppsCheck. AppsCheck provides you with information about whether the current Huawei device contains viruses and malicious apps. As for URLCheck, it can provide you with information about whether external URLs are secure. Your service logic involves information addition and message sending, making it inevitable to encounter external third-party URLs. HMS will return information about whether these third-party URLs contains network deception information or malicious apps. Lastly, UserDetect checks whether your app is interacting with a fake user, for example, a robot or a crawler. Generally, we can classify these 4 sets of APIs into 2 levels, system level and app level. SysIntegrity and AppsCheck are system-level APIs. The procedure for using them is similar. That is, you send a check request to the HMS server, and the HMS server sends related results to you. Take SysIntegrity as an example. You send a system integrity check request to the HMS server, and then the HMS server obtains the check result from the Trusted Execution Environment (TEE) and send it to you. In addition, the signature is used to ensure the reliability of the system integrity check result. Next, let's look at AppsCheck. The HMS server will provide you a list of malicious apps. The accuracy rate of malicious app detection reaches 99%. In addition, AppsCheck can detect unknown risky apps. URLCheck and UserDetect are app-level APIs. URLCheck can check whether external URLs contains potential risks, such as malware threats and phishing threats. In addition, URLCheck can efficiently check external URLs in real time. As for UserDetect, it can check whether your app is interacting with a fake user. Through the verification code technology, it can easily differentiate robots and crawlers from real users, avoiding wasted server resources. Now, let's talk about the application scenarios and a specific application of these APIs. In this chapter, we will illustrate the code practice camp. There are 3 parts in this chapter. The first part is demo overview. This part will introduce the application scenarios of the 4 types of APIs, so you can know when and where to use them. The second part is the preparation of the development environment, which mainly includes the configuration of app gallery and the integration of HMS SDK. The third part illustrates the code implementation for the 4 scenarios in the demo. In the demo overview, we introduce 4 application scenarios corresponding to the 4 sets of APIs. Let's first look at the SysIntegrity API. If your app involves operations, such as payment or core service operations, with high security requirements, you need to ensure that the environment running your app is secure. In this case, you can use SysIntegrity to check whether the device running your app is secure. For example, whether it is rooted. If the device is rooted, some backdoors and Trojan horses may be embedded in the system, leading to data leakage. In the demo, we code a button to call the SysIntegrity API. After you click this button, the System Integrity Check result will be called. After API call, the entire System Integrity Check result will be returned and displayed. Now, let's first look at the normal scenarios. In the normal scenario, the device is not rooted. Click the button. The result true is returned, indicating that the device is secure and not tampered with. Next, let's click the button on the rooted device to see the check result. In this scenario, where the device has been rooted, that is, the device has been tampered with. Click this button, then check the returned check result. As we can see, the check result indicates that the device is insecure and suggests the user to restore the device to factory settings. Through this API, your app can check whether the system is secure when your users perform core operations. Next, let's move on to the AppsCheck API. Through this API, you can obtain a list of malicious apps, so you can determine whether to limit your app's behavior based on the risk evaluation. In the malicious app list obtained from the HMS server, we can learn the risk type of malicious apps. For example, risky apps or virus apps. Now, let's demonstrate it on the device. Without any malicious apps, in this case, an empty list is returned. Then, install 2 malicious apps on the device and call the API again. First, click the button to obtain a malicious app list. After this button is clicked, the AppsCheck API will be called and returns the malicious app list. The list will be displayed below. Next, let's look at the URLCheck API. Most apps involve external URLs. For example, URLs for adding information and sending messages. For these URLs, you need to check whether they are risky. If yes, you can evaluate them and determine whether to block them or remind your users of the risks. The URLCheck API can check the risks of URLs that you enter. Currently, the API can check 2 types of threats. One is whether the URL contains malicious apps. The other is whether the URL contains network deception and phishing risks. The user can determine specific action to perform based on the risk evaluation. In the demo, we will enter some malicious URLs. Let's see the check result. Enter testing URL and click the check button. As we can see, the URL is safe, and no risk is found. Then, enter a risky URL, and click the check button again. A malicious app risk is reported. Enter another URL, and click the check button again. Let's check the result. As we can see, a network deception risk is reported. In conclusion, URLCheck can determine the threat type of a specific URL. Based on the check result, you can remind users of risks or block malicious URLs for the users. Next, let's move on to the last API, UserDetect. With this API, you can check whether your app is interacting with a fake user. If your app provides the sign-in or other functions consuming resources, you need to check whether your app is interacting with a crawler or robot based on the user behavior. Once directing that the user is possibly a fake one, the API will prompt the user to enter a verification code. If the user can enter the correct verification code, the user is a real one. In the demo, we provide the sign-in UI. After a user clicks the sign-in button, the UserDetect API checks the client environment. If the API detects that the app is possibly interacting with a fake user, it will prompt the user to enter a verification code. There are 2 scenarios for this API. One is to prompt the user to enter a verification code. The other is not. After the user enters the correct verification code, the sign-in success screen of the demo app will be displayed. Now, let's demonstrate it in action. First, let's demonstrate the normal scenario. That is, the environment is secure and the user does not need to enter a verification code. After the user enters the username and password and click the Sign In button, the UserDetect API is called too. Check whether the current environment is secure. If the environment is risky, the API prompts the user to enter a verification code. Since the environment is secure, the API does not prompt the user to enter a verification code, and the sign-in is successful. Then, let's install some risky apps in the environment, so the environment fails the evaluation. In this case, the API prompts the user to enter a verification code, so as to determine whether the user is a valid one. Now, let's practice in action. In the secure environment, we can successfully sign in to the app, and no pop-up is displayed. After we change the environment, sign in to the app again and check whether a verification code pop-up is displayed. As we can see, a verification code pop-up is displayed. If the entered verification code is incorrect, a new verification code will be displayed. After the user enters the correct verification code, the verification is successful. With the verification code, we can ensure that our app is interacting with a valid user instead of a robot. Now we finish demonstration of the 4 sets of APIs. With these APIs, you can ensure that your app is running in a secure environment. These APIs ensures the comprehensive system security from the URL check to user identity verification at the system level. Next, let's talk about the development process of these APIs in detail. This part describes relevant development preparations. The preparation consists of 7 steps. Now, let's go through them one by one. The first step is to create an app in App Gallery Connect. After registering an account, sign in to Huawei Developer. Go to Console, click App Gallery to go to App Gallery Connect and select My Apps. Here, add a new app. That is, the app to be integrated with Safety Detect. Now, let's see related parameters. The first parameter is to package type. Set this parameter to APK. The second parameter is the device type. Currently, only mobile device is supported. Then, the third parameter is the app name. The app name here must be the same for all related fields in the project. For example, the app name is Test HMS in this demo. The next parameter is the app category. Here, set the parameter to app. For the default language parameter, set it to English. After an app is created, it will have an app secret field, which indicates the app key. Later, the key will be added to a project through a file. Now we can see that the package name is still empty. Then, back to the Develop tab page and click Overview. Then you can select to manually enter a package name, which must be the same as that of the package created in your project later. Enter a package name. Note that if your app provides the payment function, the package name suffix must contain Huawei. Therefore, enter it in your package name. For example, Test HMS Huawei. Then, click Save. Now you've added the app. Then you can create a project. Let's create an Android Studio project. What do you need to add to the project? One is the public key certificates. Ensure that the project is for your app instead of other developers' apps. The other is to determine which SDK will be included in your project. After creating the project, generate a signing certificate and put the public key to Huawei developer. Now, let's demonstrate how to create a project. Go to File, New Project, select an empty activity and click Next. Here, the project name must be the same as the previous one. Back to the previous window, choose Test HMS, copy and paste it in the blank. Ensure that the project name and package name be the same as those displayed here. We can directly copy the project name, app name, and package name here. The app name and package name must be consistent. This is a generated path. Select the language. Select an earliest version. Click OK. Now the project has been created. Next, let's generate a signing certificate. In the project menu, select Dirt under Build to generate a signing certificate. Select an APK. If a signing file is available, select it. If no signing file is available, create one. Select the directory for storing the generated signing file. Here, select the directory in your project. For example, the app directory in your project. Enter a name here. For example, test HMS JKS, then generate signing file. Enter content in the signing file. Here, a password is involved. The password is used to encrypt the signing file. When opening the file again, you need to enter the password. Therefore, set a password here. Here is an alias of the signing file. Set it to test HMS. A password is also involved here. In the file, the address, city, and country of Huawei are used as an example. If you are in China, enter CN for short. Now we've configured the signing file. Next, let's set variables for build. Select both V1 and V2, which are signature for JAR and APK respectively. Then select Release. Next, let's generate a signing certificate fingerprint. To generate a fingerprint, you need to use the key2 command of Java and the JKS signing certificate. Go to the directory where the JKS signing certificate is located and ensure that Java JDK has been included in your running environment variables. Now, let's enter the key. Open your CMD window. If the JKS file is not in the path, you have to enter its full path. Now, enter the password you've just set in the path to the test HMS JKS file. As we can see, fingerprints are generated. Copy the SHA-256 fingerprint. Go back to App Gallery Connect. Paste the fingerprint in a corresponding text box under App Information on the Overview page. So far, we've added the app project to App Gallery Connect, ensuring that the project is not tampered with by others. Then, we need to integrate the HMS SDK into our project. Next, let's add the Maven repository address and App Gallery Connect plugin. Open the build Gradle file in the build directory of your project, and add the Maven repository address under build scripts in the file. Add it under all project configurations. Now, we've added the Maven repository address. Next, let's add the App Gallery Connect plugin. Open the build Gradle file in the app directory and add the App Gallery Connect plugin to the file header. Now we've configured the Maven repository address and App Gallery Connect plugin. Next, let's configure the signature. Open the build Gradle file in the app directory, and then add the signature configuration. This is the name of a configuration item. Several fields are included in config. The first one is generated signature file, that is the JKS file. The second is the alias, that is which must be the same as the previous one. Next is the stored password, which is used for decrypting the encrypted JKS file. There are two keys. One is the alias key. The other is for the JKS file. After setting these fields, add them under build types. Apply the settings to the debug version. You can repeat the configuration. Since the debug version is not included in the project, we need to add the debug version here. Configure the signature for the project. After configuring the signature, click Sync Now. Now we've completed the development preparations. Next, let's look at how to integrate the Safety Detect SDK. First, we need to enable the Safety Detect service in App Gallery Connect. On the Develop tab page, click the gear icon next to Overview and select Manage APIs. Find the Safety Detect and toggle on the switch. Now the Safety Detect service is enabled. To back to the Overview page and view information under App Information, download the app configuration file, which is a JSON file. We can open the downloaded file and check its content. Download the file to the app directory of the project. Go back to the Develop tab page and open the file. As we can see, this file contains all involved keys and app configurations. For apps with different project files, you need to use different configuration files. The files must be stored in the app directory of your project. Next, let's add the SDK dependencies. Open the build Gradle file. In the app directory of your project, add SDK dependencies to the file. You need to add all dependent SDKs to the file. As we can see, the file already contains some dependent SDKs. Add the Safety Detect dependencies to the file. Here, the corresponding Safety Detect version is 4.0. After integrating the SDK, we need to disable the obfuscation configuration. This is because the obfuscation configuration will cause exceptions of the Safety Detect SDK. Therefore, we need to exclude HMS APIs from being obfuscated. Synchronize related settings. After synchronization is completed, the Safety Detect SDK is integrated. Next, let's move on to the service development. Now let's see the Safety Detect development in action. In this chapter, we will complete the 4 types of APIs mentioned in the demo. The SysIntegrity API. There are several steps in the process. Let's go through these steps one by one. Now let's see an example of this API. To implement System Integrity Check in this API, 3 steps are required. The first step is to obtain a nonce value. The nonce value will be included in the System Integrity Check result, so you can verify the nonce value to determine whether there is a replay attack in the request. Each nonce value can only be used once, and must contain at least 24 characters. Therefore, when designing the nonce value, we should consider its uniqueness. You are advised to use the username and time as the nonce value. A user is unlikely to call the SysIntegrity API frequently. The timestamp is accurate to milliseconds. By combining the timestamp and the nonce value, you can prevent duplicate nonce values. Go back to our code. In the code, we've added the System Integrity Check button. After you click the button, the System Integrity Check function will be called. As we mentioned above, the first step is to obtain a nonce value. Here we choose the system timestamp, which is accurate to milliseconds. Combine it with a string value and choose the simple character style. In your project, you can change it to the username. After obtaining the nonce value, we start to request the System Integrity Check. We get the Safety Check object by calling the SysIntegrity API. The nonce value corresponds to the app ID, which is the ID of the app you registered with App Gallery Connect. After the calling is finished, 2 callback functions need to be set. One is successful and the other is failure, which correspond to the API call success and failure, respectively. It does not mean whether system integrity check is successful. Instead, it indicates whether the API is successfully called. There are many reasons for the failure, such as the app ID is incorrect or the SDK is configured incorrectly. If the check is successful, we will receive the system integrity check result. After obtaining the result, we can do several things, including limiting the user's behavior or performing some local operations. Then, send the check result to the server can check whether the app running environment is secure. Here we go to the client at first. Let's see what to do next after receiving the result. You need to send the result to the server based on your business requirements. Then, let's see how can we get the result. First, we create a listener function named onSuccess. This function obtains the receives GWS format data through the response. We can save the GWS format data as a string because it is encoded using base 64 and can even be passed on the browser address bar as a parameter. The result consists of 3 parts: header, payload, and signature, which is the basic GWS format. The 3 parts are separated using dots. Since a regular expression is passed, there are 2 slashes. One slash is passed to the regular expression and the other is for separation. The first part is the header and the second part is the check result. So we can obtain required data from the second part. Let's decode it using base 64. The data is in the URL safe format, that is, converted using base 64 URL. Since %size and equal signs in the URL will be converted, the string obtained after conversion is a JSON string. Therefore, we directly parse the JSON string to obtain the check result. After obtaining the result, we can show the user whether their system integrity check is successful. If the result is failure, we can obtain a suggestion, which is contained in the check result. For details about the parameter type, please refer to the official API reference. The returned header specifies the signing algorithm. The second piece of information we can learn is a signing certificate chain of the Huawei signing server. This is the payload of GWS, which contains a nonce value. Now we can verify the nonce to see if the request is the one we sent. It contains the timestamp, package name, and abstract of the signing certificate. The last one is the suggestion. After receiving the data, you can do corresponding work. How can we ensure the data and operation security? We need to send the data to the server for verification. The server will check whether the data is tampered with and whether it is for the request we sent to prevent replay attacks. Therefore, we need to verify nonce in the code. When your app gets the nonce data, it should forward it to the server for verification. Let's have a look at the code on the server. The server parses the data to obtain the header and the signature from the GWS format data. Let's look at the verification process. The client app sends the data to the server. The server needs to verify the certificate chain. First, to ensure that certificate is officially offered by Huawei. We can do this through the root certificate of Huawei. After verifying the certificate chain, we will verify the domain name of the certificate in the certificate chain, then verify the signature. We get the public key from the certificate and configure it. Then, use the sub-public key to verify the signature in the GWS data. Finally, the server will send the verification result to the app. After completing these actions, we are sure that this message is not tampered with. Now we have finished the home process of system integrity check. If a user performs an operation in the app client, the app client will send the check result and the nonce value to server. After the server verifies the result, the app can evaluate the check result and decide whether the operation is allowed. So much for the system integrity check. Let's move on to the next part. Here's an AppsCheck API demo. It shows how can you call the API. Step 1. Obtain object for check. Step 2. Call the AppsCheck API to obtain a list of malicious apps. Add a success listener. After a successful call, the HMS server will return a list of malicious apps. We can get parameters from the list by the type of these apps. Based on API reference, we can learn about how to obtain the name and the category of malicious apps. In the API reference, we can see the returned malicious app list, including name, type, and the base 64 encoded SHAR56 value of malicious apps. Malicious apps are classified into risky apps and various apps. According to your app's security level, you can determine whether to limit its running or not. Since this API returns a list, it is convenient to display the result or judge it. That is the AppsCheck API. Next, let's look at the URLCheck API. Malicious URL check also consists of 4 steps. Initialization. CLL the URLCheck API. Request the URL check. Close the URLCheck session. Deal with the error code. Let's first see initialization. After obtaining object using Safety Detect get client, call init URLCheck for initialization. When a user visits a URL, the URLCheck API is called. The URL contains several parameters. The first 2 parameters are the URL to be checked and app ID. URLs to be checked are classified into 2 types: URLs containing malicious app downloaded links and URLs containing fraud information. After the API is called, add on success listener to obtain the check result. The check result is a list. If the list is empty, the URL to be visited is secure. If the list is not empty, we can learn about the risk types of the URL to be visited. Now we've completed URLCheck development. Next, let's move on the last API, UserDetect API. The code also consists of 2 parts. One is that the client called API and displays the obtained result. The other is that the server displays the final result of the fake user detection. Code implementation on the client consists of 2 steps. The first step is to initiate the fake user check request. The second step is to get the check result. Call the UserDetect API and initial a check request. The API will return a response token. The response token will be used to check whether the verification is successful or not. If user's environment is considered to be insecure, a verification code pop-up will be displayed. After the user enters the verification code, a verification success response will be returned. Let's look at the process. Your app initializes a request to call the UserDetect API. The API interacts with HMS server to check whether the user's environment is secure and generate a token. If the user's environment is insecure, a verification code pop-up will be displayed. After the user enters the correct verification code, the HMS server determines that the verification is successful. Meanwhile, after your app obtains the token and verified it successfully, your app will send the token to the server. Then, the server checks whether the detection is successful through the token. That is why our code implementation consists of 2 parts. First, let's see the code implementation on the app. The code first initiates a detection request to obtain detection object. Call the UserDetect API and pass the app ID to add the success and failure listeners. Generally, the detection fails when some exceptions occur. For example, the server connection is incorrect, the pass the app ID is incorrect, or the permission is not enabled. Now, let's look at the success scenario. After you add the success listener and call the UserDetect API, HMS will determine whether to display a verification code pop-up based on the user environment. If a pop-up is displayed, Unsuccess is triggered only when the user enters the correct verification code. If no pop-up is displayed, unsuccess is triggered directly and a UserDetect response object is returned. We can get a response token from the object. Then, we can send the token to the server. For sign-in, we will send the username and password as well as the token to the server. In the code, the post method is used to send the username and password as well as the token to the server. The server verifies the token first. Now, let's move on. Look at the process. The app initiates a UserDetect request to call the HMS API. The HMSS API checks the user's environment and sends the check results to the HMS server. The HMS server checks risks of the environment, generates a token, and sends it to the HMS. If the environment is risky, a verification code pop-up will be displayed in the app. After the user enters the correct verification code in the app sends the token to the app server, which forwards the token to the HMS server for verification. Then, the HMS server sends the verification result to the app server. After verifying the result, the app server will perform related service processing and sends the result to the app. Code implementation on the server consists of 3 steps. The first step is to get an access token. The access token is used to verify your identity when your app calls the cloud APIs of Huawei. Now let's have a look at how to obtain an access token. In the code, OAuth is used for sign-in verification. Here, the address, the OAuth authentication address of Huawei. We need to provide the app ID and key, and authentication type. As for the app key, we can directly obtain it from the background of Huawei developer. After setting the app ID and the private key, we encrypted the request using SSL and then send the encrypted request to the authentication server of Huawei. After successful authentication, Huawei will send you an access token. The access token is required for all later operations. The access token has a validity period. With the validity period, you can use the access token to obtain the fake user detection result. This is because the app has sent the response token to us. You need to verify whether this token is risky. After receiving the response token, you need to send the access token and response token to official authentication server of Huawei through HTTPS. If success, we will send back the result. Of course, you need to implement your service logic. If the detection fails, we will send you a message indicating that the fake user detection fails. We implement the service logic when the detection is successful, and then returns the service logic to the app. Now, we've completed the fake user detection process. In this demo, we've completed the call of the 4 sets of the APIs of Safety Detect. In addition, interaction between the app and the server is involved. During app development, you can select related APIs to integrate based on your service needs. We have shown you the demo and the source code. You can learn more details by debugging the source code. Finally, you can build an app with high security. That's all for this course. Thank you for watching.